Okay, dah start.
Okay, Assalamualaikum warahmatullahi taala wabarakatuh. Today we are from Network Analysis student from group LO2 BO2. We are going to perform completing our assignment, which is the application of Fourier transform. First of all, we are going to introduce our name first. First, my name is Muhammad Fakrul Syahmi bin Jamal.
My name is Afiq Syahmi bin Azril Shuaini.
My name is Muhammad Muizzuddin bin Munzir.
Muhammad Iqbal bin Syamudin.
My name Muhammad Nazmi bin Lilisman.
Okay. So today we are going to present about the application of Fourier transform in electrical engineering and medical field. So we go through to the introduction. First of all, we go through to the introduction of Fourier transform. Fourier transform has named after Joseph Fourier, which is the mathematical transformation employed to transform signal between time or spatial domain and frequency domain. Any periodic signal wave can be represented as the sum of a series of sinusoidal wave of different frequencies and amplitudes. Concerns with periodic wave, the periodic wave may be rectangular, triangular, sawtooth, or any other periodic form or single value. Sinusoidal wave or different frequency and amplitudes add to give a periodic wave of non-sinusoidal form. So, the Fourier transform is a mathematical operation used widely in many fields. In medical imaging, it used for many applications such as image filtering, image reconstruction, and image analysis. Fourier transform is an operation that transforms one function of a real variable into another, where it called the new functions as a frequency domain representation of the original function that describes with frequencies as present in the original function and decomposed into oscillatory function as an effect. The Fourier transform is a fundamental mathematical tool widely used in signal analysis, as it is present in radiology and integral to modern MR image formation.
So, application of Fourier transform in electrical engineering. This is the formula for Fourier transform.
The application of Fourier transform in electrical engineering. First is a mathematical method to convert a function in the amplitude vs time domain to the amplitude vs frequency domain for non-periodic function. In electrical engineering, there are several instances where one deals with signal, waveform, and manipulation of signal. The manipulation may be any operation such as additional, multiplication, differentiation, integrate. This manipulation may be a result of a tangible electrical circuit RC, LC, RLC, or simply an abstract system. Hence a strong analytical method is needed to examine the result and side effects.
How do Fourier transform work? It takes two signals and puts them together to make a new signal. The Fourier transform returns a representation of a signal as a superposition of sinusoids. Fourier transforms are used to perform operations that are easy to implement or understand in the frequency domain, such as convolution and filtering. Why is working is in frequency domain so important? Because a lot of time we have desired signal and undesired signal mixed together, and we want to be able to separate them. Those signals are often in different frequency, so they are easy to separate in frequency domain but hard to separate in time domain. For example, we can filter out high frequency, less noticeable detail in image to perform image compression. That's how JPEG and most other intra-compression algorithm work.
Okay, we can also separate out background noise from conversation in audio recording if they have different frequency profile. They often do. We can also do things like transmitting many RF signal at the same time on different frequency and have a receiver use filter to decide which channel to listen to. We can also separate out background noise from conversation in audio recording if they have different frequency profile. We can also do things like transmitting many RF signal at the same time on different frequency and have the receiver use filter to decide which channel to listen to.
Okay, this is the example of the circuit that we have applied Fourier transform based on the class, and this is the one of example that have been shown by our lecturer, Madam Nozani. So from the circuit we have know the method. We have the three method, which is the first method we must to convert the T domain to omega domain for the first method, and the second method we must to find the V out omega, and the third method we can see from the slide is we must to inverse the Fourier transform, which is the V out omega, and lastly we apply the partial fraction. So we can get the value from the partial difference, and this is the example of the calculation that we have discussed, referring the calculation from our lecturer Madam Nozaini. This is the same method that we have used. First of all, we have to convert the T domain to the omega domain, as you can see from the example of the calculation that I have shown on the slide. And next, we must to find the VR omega, and then we apply the inverse Fourier transform, and lastly we find the value, use the partial fraction, and you can see the value of V out in the slide. That's all the how the calculation done with the Fourier transform method. Next, application of the Fourier transform in medical field. Medical field mostly dealing with electromagnetic wave. Fourier transform is a mathematical technique that allows MR signal to be decomposed into sum of sine wave of different frequencies, phases, and amplitude. This is I have explained twice, and the first I have explained on the first introduction. Okay, next.
Right, for the application of Fourier transform in medical field, the Fourier transform allow MR signal to be decomposed into the sum of sine wave of different frequency, phase, and amplitude in a mathematical technique and used to reconstruct the image from this raw data. MRI machine take an image of the human body and produce signal from all the tissue in the scanner, where the output is in the form of raw data where it illustrate the ability of the multidimensional Fourier transform. The images are taken as the object placed in the magnetic field where it is take the alike and the the, the alike atoms in the object. In the Fourier transform, it will collect the MR image encoding filling of K-space and a wide spectrum of artifacts as it will resolve the frequency and the encoded MR signal that compose K-space. The 2D inverse Fourier transform of K-space is the MR image measure, and it is an array of numbers representing spatial frequency in the MR image. The Fourier transform reserve the frequency and phase encoded MR signal that compose the K-space. A line of data correspond to the digitized MR signal at the particular phase encoding level. The position in K-space indirectly related to the gradient across the object being imaged. By changing the gradient over time, the K-space data are sampled in a trajectory through Fourier space. Every point in the row data matrix contains part of the information for complete image. A point in the row data matrix does not correspond to a point in the image matrix. The outer rows of the data matrix, the higher spatial frequencies provide information regarding the borders and contour of the image, the detail of the structures. The inner rows of the matrix, the low spatial frequency, provide information on the general contrast of the image.
Yes, so as you can see here, there is a difference in the brightness of the image. You can see that it is very bright, and then followed by a darker and more bright and darker image. So in order to get these, next. Okay, so in order to get these, you use the 2D Fourier transform formula, which is x omega 1 omega 2 equal to the sum of n1 equal to infinity, n2 is equal to infinity, and x n1 n2 e to the power of negative j omega 1 omega 1 n1 times e to the power of negative j omega 2 n2. So the other formula is used if you want to know the image of the space. But for in this case, you just want to know how the raw data coming from the MRI being converted into the frequency wave. So for example, you see on the left graph, the left figure, you can see there are 5 plots in the K-space. So here, you use the first formula, the H omega 1 omega 2. So in order to get H n1 n2, n1 n2 comes from the plot of the dots. So there are 0 0, negative 1 0, 1 0, 0 1, 0 negative 1, and 0 1. So we plot the n1 and n2s in the formula. So you get the H, okay, so you get the H 0 0, and e to the power of 0 is 1, and then H negative 1 0, e to the power of j omega 1 and 1, and 1 is negative 1, so you times with negative, and so on and so forth. So from here, H00. The H00, you use the value over here, and then you substitute it into the formula. So this is 1 over 3, this is 1 over 6, and then H10 is 1 over 6, and so forth. So from this 1 over 6 e to the power of j omega times plus 1 over 6 e to the power of negative j omega, you can combine these two and then make it into 2 cos omega 1. So this one e to the power of j omega 2 plus e to the power of negative j omega 2. You combine these two and you get 2 cos omega 2. So from here we can simplify the equation into 1 over 3, then bracket 1 plus cos omega 1 plus cos omega 2. Okay. So here is the image of the k-space. So here is the frequency formula that we use. So here is the plotted graph of the formula. So as you can see over here, the density over here is very high compared to the lower one and lower until it dips to 0, and then it rises back up. So what you can get from here is that over here is very bright, and then the brightness decreases as it spreads out through the image until it goes to black, and then it rises back to being white. So if you refer back to the previous couple slides,
Okay, this is the formula.
okay, so you can see that the intensity over here is very high. That is the peak of the graph before, and it goes into black is the, the lower value, which is 0, and then it rises back up into it shows some whitish color. So that's how the MRI is being transformed into the image. Okay. That's all.
Okay, next we go to the formula. This is the example of the formula that used in MRI. So next, this is also the figure, the example figure of the application of Fourier transform in medical field. Okay, the application of Fourier transform in medical field. The quality of medical image is as good as it clarify of the specific information sought for in the image by the observing the physician.
Define objective image quality. Features to assess the quality of the image produced by an imaging system or by an processing technique.
Okay, we also can get the better image for the result. Okay, this is the process for the MRI. First, from the Fourier transformation to spatial frequency, and next to the 2D Fourier transform and MRI image reconstruction to the K-space, and next to the gradient and spatial frequency, and next to the linear trajectory through K-space. This is the example of the figure that can show the time domain change to the frequency domain. The Fourier transformation is the mathematical procedure which is connecting the time domain which is ST and the frequency domain as omega. So from the research that we have go through, we can discuss the time domain signal of the square wave, which is the ST. The frequency domain representation is the S omega. So we can see from the figure, the S omega is called the Fourier transform of ST. In general, S omega is a complex value function composed of harmonic frequencies, phases, and their amplitudes obtained from the Fourier expansion. This is the example of the Fourier and K spaces. Fourier transform of a black canvas, which is on the left, and the white and the one bright dot at the origin in the Fourier space, which is on the right. Okay, for the conclusion,
The conclusion is represent most powerful analytical tools in many fields, help to describe the physical mechanism of collecting and reconstructing data. It also become a priceless image processing instrument in other areas which are related to biomedicine.
extremely useful in all fields of science and technology, such as applied mathematics, physical science, and engineering. Fourier transform method has long been proved to be extremely useful in all fields of science and technology, such as radio astronomy, seismology, spectroscopy, crystallography, medical image processing, and signal analysis technique. So that's all from our group. We have shown what we have discussed on the application of Fourier transform on the electrical engineering and the application of uh, Fourier transform on medical field, which is we have shown to you the application of medical field on MRI. That's all from us. Thank you.